So now that we know that, how do we actually construct it? Okay. And I will argue to you that you already know how to construct a confidence interval by everything that we've learned up through this point. I made the comment very early on that chapters 1 through 7 are just building foundation. And now that we have that, we actually know how to build a confidence interval. So what we're going to do now is we're just going to put all the pieces that we've learned from before together now in one place. And I'm going to illustrate to you, you already know how to do this, even if you don't realize you do. A confidence interval is constructed by adding and subtracting a margin of error to our point estimate. And so you say, okay, we're going to add and subtract something to our point estimate. Now, my point estimate, we already know that. We covered that at the start of this chapter, right? A point estimate is going to be the best guess that I have at an unknown parameter. So if I have a problem that says I need to find a confidence interval on P, my point estimate's P hat. And if I have a problem that says I need to find a confidence interval on mu, my point estimate is X bar. So that's for the first part of a confidence interval is start with our point estimate, and then I need to add and subtract a margin of error. And now you say, wait, margin of error, I don't know how to find that. You lied to me. We can't do it yet. Say, okay, hold on. A margin of error is defined by taking a critical value and multiplying that times the standard deviation of the point estimate. You say, well, there's a lot happening there. Let's hold off on critical value because we're going to cover that next. We're going to say take a critical value multiplied by the standard deviation of the point estimate. You say, well, what do you even mean by that? And I would say that's something we've already covered too. We covered that in chapter 7. The standard deviation of the point estimate harkens back to chapter 7 when we said if we needed to find a probability involving p hat, we had to know what the distribution of p hat was. And we said, that p hat would be approximately normal under the right conditions with a mean of p and a standard deviation of p times q times n. So the standard deviation of the point estimate in a p hat problem is that square root pqn that we were using last chapter. And for a mean problem, we did that last chapter as well. We said that x bar would be either exactly or approximately normal, depending on the conditions, if the right thing's held, with a mean of mu and a standard deviation of sigma over square root of n. And so we've been working with standard deviations of point estimates, right? Because point estimate is just a best guess. It's just the right statistic for the problem. So what that should read in your head is critical value times the standard deviation of either p hat or x bar. We did the standard deviation of x bar last chapter. We did the standard deviation of p hat last chapter. So you already have those pieces. You already have those formulas. And you say, okay, but this critical value thing, that's a new term. So yes, it is a new term, but you already know how to find critical values too. You just don't know it yet. All right, but a critical value is just a cutoff value. Okay, we found cutoff values in chapter 6 and 7. A critical value is a number that separates sample statistics that are likely to occur from those that are unlikely to occur. Okay, it's this idea that if I were to say, I want to flip a coin 100 times and I want to record how many heads I got, how do I know what's likely versus what is unlikely? Because I think we can all agree, yeah, I would expect to get 50 heads, but that probably wouldn't happen, right? I might get 51 or 52, 49, 48, whatever. So 52, totally fine. Like if I flipped the coin 100 times and got 52 heads, you wouldn't blink an eye. But what if I got 54 heads? Would you say that's okay? What if I got 56 heads? What if I got 58 heads? What if I got 59, 60, 61, 63, 65, 67? Where do you draw the line? Right? I think we all can agree that if I got, say, like 85 heads, you'd say, wait a minute, something's off with either the coin or the way you're flipping it. But where would I draw the line at? Okay, and that's what a critical value is. It's a cutoff. It's how do you make a cutoff between what's likely and unlikely to occur. We're going to notate it with an asterisk. So anytime you see a letter with an asterisk, that is a critical value. And specifically, we're going to also subscript it with what the area is that we're trying to cut off. All right. If you think back to chapter 6, we learned about finding cutoffs, and when we found cutoffs, we always had an area to the left and the right. We might not have talked about both, but we did, right? We found a cutoff value for, say, the 60th percentile, and the 60th percentile means 60% of the values were less than that, 40% or more than that. That was one way we found a cutoff value. We found a cutoff value by finding quartiles. We said that quartile meant that there's 25% of the values less than that and 75% greater than that, right? So we were able to find these cutoffs, and they always had an area to the left and the right. And so when we find critical values here, we're going to notate them with the appropriate letter. We'll get to that in a second. We're going to add an asterisk, and we're going to subscript them with the area that we're using to find that cutoff. Because when we found, say, the value for the 60th percentile, we knew 60% of the values were less than that, but that wasn't the answer, right? The answer was, what was the z-score that cut me off there? Or sometimes I had to translate it back into an x, right? I could find the z-score that cut off 60% of the area to the left, but then sometimes we unstandardized it back to an x, remember? So in this case, we're going to be thinking along those same lines, but the benefit here is we don't have to unstandardize back. We get to stay in z. Okay, so we're going to say z asterisk alpha over 2 is a z critical value with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. I've drawn a little picture there for you. It's this idea that when we build a confidence interval, we have to have an upper bound and a lower bound, and we have to cut off some of the values to the right and some of the values to the left. Our significance level is alpha, and we have to put half of that alpha in the right tail and half of that alpha in the left tail. So that's why we talk about this alpha over 2. We're always going to be cutting our alpha in half and saying that I need to use that as my area to the left or right in order to find critical values. Because the z distribution is symmetric about 0, notice that critical value on the right is just going to be the positive version of the critical value on the left, which will just be negative. And so a couple quick examples. Find the critical values for the following confidence levels. We're going to start off with 97% first. A couple ways you could think about this. Might want to draw a picture. Might help you out a little bit there. If you look at the picture above that in your notes, kind of mimic that. I can take my confidence level. If you want, you don't have to. You can put that in the middle of the curve and say 95% confidence, that's going to be 0.97 in the middle. How do I know that? Well, my confidence level and my significance level have to add to 1. The total area under the curve adds to 1. And so if I look at that picture and I put 97% in the middle, I subtract that from 1 to get 3%. That's why we have that alpha over 2 in both tails. My alpha, my significance level for a confidence level of 97% would be 3%. Cut that in half, that means we have to have 1.5% in both tails. And you can double check to make sure that adds up to 1. 1.5% plus 97% plus 1.5% would get you to 100%. Now do note that we typically refer to our significance level in decimal, whereas we typically refer to our confidence level as percent. Okay, so if we're looking for a 95% confidence level, that's a significance level of 0.03. Put half of that in both tails like we just talked about, that's 0.015. And you can find the left one or the right one, it doesn't matter. Make sure you understand if you find the left one, then that means the area to the left of that point is 0.015. If you find the right one, because the area to the right is 0.015, we'd have to subtract that from 1 to find the area to the left. That'd be 0.985. And now here's the catch. You got to make sure you don't stop there, right? All we've done so far is convert our confidence level to a significance level and then cut it in half and talked about what the area to the left of those critical values happen to be. We've only got area to the left now. We still have to finish this off. We find cutoff values by saying what's the area to the left, going inside the z-table, finding the value closest to that and seeing what z-score that corresponds to, just like we did in previous chapters. And if you look up 0.015, you'd get the value negative 2.17. If you look up 0.985, you'd get the value positive 2.17. And so our two critical values, there's two of them, because we have to have one on the left, one on the right, plus and minus 2.17. Again, you can find either one of them because we are in the standard normal. We know that everything that happens on the right is just the positive version of everything that's negative happening on the left. Remember, that doesn't hold if we're dealing with just normal x values that happen to be normally distributed. But because we're in the z, we have that added bonus of knowing that about how a z works. Do the same thing for 95%. Go ahead and put 95% in the middle if you want. We have to take our significance level. That would be 5%. Cut that in half to 0.025. Either look that value up or look up the value 0.975 if you wanted to find the positive one. Again, either one doesn't matter. And you should get plus or minus 1.96. Last one, 90% confidence. Here we just have to be careful with zeros when we move in decimal places that we don't add or lose some of that movement of some of those leading and trailing zeros. 90% confidence level would be 10%. Significance level, that would be 0.1. And so then we cut that in half, that's 0.05. If I look up 0.05, or if I wanted the right one, look up 0.95. And that looks like it falls smack between negative 1.64 and negative 1.65, or on the positive side, positive 1.64 and positive 1.65. And that value actually is right in between. Now, what I want you to understand here is, just like we talked about before when finding cutoff values, we don't actually interpolate to that third decimal place. What we do is we find the closest. It's not about above or below. We find the closest one. And I know that in this case you say, but it's right in between. If it's right in between, just pick one. If not, pick the closest one. Or if you wanted to, you can go to Excel and you could find the value and actually do the third or fourth decimal place. This is a special case in that if you go to the bottom corner of your z-table, you will notice a box that says something like critical values for confidence intervals. And you will see that it says that for a 90% confidence interval, my critical values are plus and minus 1.645. For a 95% confidence interval, the critical value is 1.96. For a 99% confidence interval, it gives that value as well. So we can go ahead and use that as a cheat sheet for the most common critical values. And that's how I got that third decimal place. That's the only reason why I used it. Otherwise, I would not interpolate. Otherwise, I would just go ahead and say, my z-table gives me 2 decimals, I'm going to report 2 decimals. The only exception is if you're using that bottom corner where it gives you those pre-done critical values for confidence intervals. What I want to make sure you understand is that that bottom corner is helpful for finding critical values for the most common confidence levels. However, you still need to be able to find critical values for things not in that little box down in the corner. Okay, so for instance, finding the critical values for a 97% confidence level like we did in this example, do not forget how to do that. So be able to find critical values for confidence levels that are odd, 96, 97, 94, 93, those type of things like that, be able to find those as well. But most of the time we will be using those common ones that are listed in the bottom corner.